go. Share screen. Okay, and we'll continue on with this. Just as a reminder, we're going to, oops, that's not what I wanted. I wanted this. We're going to continue on with this review on Thursday morning at 8 a.m. If you can attend, I would love to have you. And of course, if you're watching this as a video posted to D2L, no problem. I will post the video link for all of these exam reviews. So let's take a look at question number 32. This is where we left off. It says, given a diagram, determine which diagram looks like a strong acid. So a strong acid, this is again written by Dr. Garcia. She really likes to use exclamation points and capital letters. You need to know that a strong acid will dissociate completely, right? And this is a question that was in one of our pre-labs, supposed to dissociate completely. So a strong acid will do this. It's going to dissociate completely into H plus and A minus. So that's why everything is broken apart into its ions like this. If you had a weak acid will only partially, we'll put dissociates partially, okay? And that's when we use the reversible arrows like this. So you would have some of H plus and some of A minus. So what would that look like in a solution, right? If you had a solution, you'd have some H plus and some A minus and some H plus and some A minus, but you'd also have molecules that are still intact, right? Anyhow, artist's rendition. Okay, number 33 says review the colligative properties. And so you should understand that colligative properties are based off of the amount of particles of a solute added to a solvent. And the colligative properties that we look at in Chemistry 101 are osmotic pressure. You might have seen this formula. Osmotic pressure is equal to molarity times the gas constant times temperature. I don't believe there's any questions that ask you to calculate osmotic pressure, but it's a good idea to understand what osmotic pressure is. Then we look at melting, boiling, and freezing. So in terms of melting and freezing, we look at freezing point depression, and then we also look at boiling point elevation, and we also look at how vapor pressure is affected by solute particles. And so what's going to happen? Let's discuss these quickly. Again, osmotic pressure, I don't think there's going to be any questions about that. But if we think about the freezing point of water, what's going to happen when I dissolve a solute and put it in water? Well, a solute is going to affect the freezing point of water in that it's going to lower it. And that's why we talk about freezing point. We'll put freezing point depression, right? It lowers, not deep, I'm thinking about too many things at once here. Depression. And then in terms of boiling point, we have boiling point elevation. So the boiling point would be higher. Okay, and then in terms of vapor pressure, we get vapor pressure lowering. And so again, I don't think there's any questions about calculating these, like your delta TF or your delta TB, but you should be aware of the effect of adding a solute to a solvent. So make sure you review colligative properties. All right, moving right along. Question 34, given a mass and a molecular formula, you should be able to determine the number of moles. So it says, how many moles of limonene are there in the 300 milligram dose? Well, I'm assuming that the essential oil is all limonene. And the first thing that you have to do here is determine the molar mass of limonene. So I add up the mass of 10 carbons and 16 hydrogens. I've already gone ahead and done that, and it's 136.24 grams per mole. And of course, we know that molar mass is equal to grams per mole, so it's equal to mass divided by number of moles, and we can rearrange that and solve for number of moles, and therefore number of moles is going to be equal to the mass divided by the molar mass. And so we have our mass, but it's given to us in milligrams, so we need to convert that into grams. And so we'll say 300 milligrams, and we know that in 1 gram we have 1,000 milligrams. So milligrams cancel out, and we end up with 0.300 grams. Now we can plug this into our formula. So I'm kind of running out of space here, aren't I? I'm going to erase, I'll erase this just to make it look prettier. Okay, and I have that my mass, which is 0.300 grams, divided by my molar mass, which was 136.24 grams per mole. And my mass units cancel out, and I end up with the number of moles being equal to a small number, which is 2.20 times 10 to the minus 3 moles. And again, I think this is the kind of question that if you tried or attempted the practice problems, that you wouldn't struggle with that too much. Let's take a look here. You have to know the difference between crenation and hemolysis. So crenation is when the red blood cell shrinks. So it's when it shrinks, and crenation occurs because the red blood cell is put in a hypertonic solution. And what that means is that the solution has a greater concentration of ions than the concentration of ions inside the red blood cell. Remember, a red blood cell or a human blood cell has a semi-permeable membrane. Semi-permeable. That means only the water can flow across that membrane, and ions cannot flow across that membrane. So if the red blood cell is placed in a solution that has more ions in it, the water is going to flow out of the red blood cell. It's going to shrink, and again, we call that crenation. Okay? If I put a red blood cell in a hypotonic solution, which means the concentration of ions is less than that inside the cell, the water molecules in the plasma or whatever medium the red blood cell is in are going to flow into the red blood cell to try to balance out the concentration, which is going to cause the red blood cell to burst. So hemolysis is like when it explodes, so burst. Okay, I know the slide that's in our slide deck doesn't show the blood cell bursting. It's more showing it like blown up like a balloon. Anyhow, so you should know the difference between a hypertonic and a hypotonic solution, and you should know about the concepts of crenation and hemolysis and what kind of solution they occur in. And you should also know that a red blood cell contains or possesses a semi-permeable membrane. The next question says what? Something. It says, given an ionic compound, determine the charge of a cation. We already did a question very similar to this in the first part of the lecture. You should always remember that oxygen almost always has a charge of -2. So we have O2 minus, and if there's 3 of those times 3, we're going to have a total of -6. And so that means that for my cobalt, it would have to be +6, but there's 2 of them. So it must be cobalt 3+, okay? And again, we went over this earlier in another question. So I'll kind of go over that one quickly and move on to the next one. The next one is just conceptual. She wants you to remember what? It says here, given the concentration or given a concentration in percent weight over volume, determine what happens to the concentration of that solution when some of the solution is poured into a different container. And I hope that you're all just thinking, well, nothing would happen, because that's the answer, right? If you're taking a solution, right? If you take some Kool-Aid in the pitcher, and let's say you have concentrated Kool-Aid in a pitcher, and you pour it into a glass, it's still the same concentration. You didn't dilute it just by pouring it, right? So the answer to this one is nothing happens to the concentration. Nothing. Okay. Nothing happens. Okay. Given a list of compounds, determine the ionic compound. This, again, she's repeating herself here. This is something that we've looked at already. An ionic compound is made from a metal and a non-metal, or a metal and a polyatomic ion. If you're like, what's an example of a metal and a polyatomic ion? An example of that would be something like, let's say, sodium sulfate, Na2SO4, right? Because Sodium is a metal, right? But the sulfate polyatomic ion is made of nonmetals, right? Because sulfur is a nonmetal and oxygen is a nonmetal. So that would be an example of an ionic compound made from a metal and a polyatomic ion. The next one deals with different types of reactions that we looked at. So a synthesis reaction is when you combine two elements. So basically you start with more components and you end up with less. Sometimes we call these synthesis, sometimes we call them combination reactions, so combinational. In fact, I think that's the word that's used in our book. If you take one, thing or one substance and you break it down into more substances, this is called a decomposition reaction. The next one says if you take a hydrocarbon is something that's made from carbon and hydrogen. The reason that hydrocarbons are so important is because petroleum and crude oil contains mostly hydrocarbons. So that's a big part of the industrial chemical industry, I should say. If you take a hydrocarbon and you add that to oxygen and it produces, this should be an arrow, produces carbon dioxide and water. There's a bunch of different ways you could label this reaction. It is, not only is it a combustion reaction, but it's also a redox reaction. So there's all of these different types of reactions. They're not always mutually exclusive. So there's a couple of ways you could label this one. And then of course the double replacement. I remember explaining this to my class, I said it's like a square dance, swap your partner around and around in a hey and a ho. So a double replacement. Also, one that's not on here is the single replacement. Single replacement. So if you're unsure about what that is, you could take a look at that one. I won't give you an example. I'll make you do some of the work. All right. Just give me 1 second here. You guys can look at the next question, which is question 40. Actually, this is a concept. All right. Given a list of solutions, determine which solution is a heterogeneous mixture. In a heterogeneous mixture, you can clearly distinguish the two or more different substances. So let's say you mix up some sweet potatoes and marshmallows. That sounds horrible, but that would be a heterogeneous mixture. Let's come up with a better example. What about salt and pepper? Right? If you mix salt and pepper, you go to Subway sandwiches, they have a special shaker where they combine salt and pepper. It's a real, breakthrough in terms of technology, mixing those two seasonings together. But you can see the salt and you can see the pepper, right? They're not mixed completely to one phase. You can see the individual particles. So that would be a heterogeneous mixture. Like chili would be a heterogeneous mixture. What else? If you look at marble, right, you can see different minerals in the stone, so to speak. Anyhow, and a homogeneous mixture would be something like coffee or iced tea or Coca-Cola or Kool-Aid. It's not too concentrated, of course. It's not a saturated solution. So again, you should be able to identify a heterogeneous mixture and a homogeneous mixture. But that's something we looked at in quite a bit of detail, or Dr. Diaz would have looked at that in even more detail. What else? Rules for bonding. This is a big one, is Lewis structures. We spent a lot of time in face-to-face lecture. I'm looking over here on my wall at where we finished up, where we kind of finished the class in terms of face-to-face, and it was after chapter 5. So we spent a lot of time looking at the structures of compounds and determining molecular geometries. Whenever I teach Chemistry 102, the first thing I always tell those students, the first day, I always figure, you remember what the instructor says in class for the first couple of minutes. After that, who knows who's paying attention. But something you should know is that carbon always has 4 bonds. It always has 4 bonds and no lone pairs. An example of that would be something like CO2. So if I write out the Lewis structure for CO2, right, you can see the carbon has 2 double bonds, but it has a total of 4 bonds. Another example would be something like methane, CH4. CH4 has 4 bonds, and we could keep going with that, but we won't. The next one says the nitrogen family. Nitrogen always has 3 bonds in 1 lone pair. Like if you look at the Lewis structure of ammonia, the nitrogen has 3 bonds in 1 lone pair. If you, oops, I didn't mean to do that. If you look at something like, come on, what did I press here? Something like methylamine. So this is just another Lewis structure. Methylamine is the amine that smells like stinky fish. Okay, again, you can see that the nitrogen atom has 3 bonds in 1 lone pairs. Water, hopefully you've all figured that out by now. The oxygen always has 2 bonds in 2 lone pairs, right? Whether it's in a Lewis structure like this, or even if it's got a double bond, you see this oxygen atom still has the 2 bonds in the 2 lone pairs. And then the halogens, chlorine, fluorine, and bromine, they always form 1 bond. So an example would be something like HCl, right? The chlorine has 1 bond, 3 lone pairs. HBr, right? Still has 1 bond. HF, and you could do the same thing with HI, right? Whatever. They always have 1 bond and 3 lone pairs. The idea is that you've seen enough of these by now that you should know this, with relative ease if you've practiced enough Lewis structures. The next one, electron configuration. This is an old chestnut. When we looked at the structure of an atom, we talked about what electrons, protons, and neutrons are. We discussed the history of those subatomic particles. And then we discussed how electrons are arranged in orbitals. And we talked about what an s orbital, a p orbital, a d orbital, and an f orbital are. And then we discussed electron configuration. So it says here, what is the electron configuration for the element nitrogen? Well, nitrogen is element number 7. So it has 7 electrons. We start on the first row, which is the first period, and there's 2 electrons. They're both s electrons, so it's 1s2. So that's 2. We have 5 electrons to go. We go down to the second period, we have 2s2, and then we have 2p3. Now, again, this is a loaded conversation, right? We could sit here and talk about electron configuration for the next 25 minutes. But and this is something that we went over in a lot of detail in class, so if you're unsure about electron configuration, it might be wise to review that before the final exam on May 12th, which is a week from today. Moving right along, question number 43 says, given a structure capable of resonance, determine the number of possible resonance structures. So it says here, how many total resonance structures are possible for the carbonate ion? Let's start by drawing the carbonate ion. And this is also something that we did in class, but I'll refresh your memory that the carbonate ion, remember our oxygen our carbon must have 4 bonds. We have 1 oxygen that has 2 bonds and 2 lone pairs, but the other oxygens are exceeding the number of bonds. They still have an octet, but they have 3 lone pairs and 1 bond, and both of them have a negative charge. Now that is not covered in our textbook, but I taught you how to do that. And the way you determine that is you take the number of valence electrons, and then you subtract the number of sticks and the number of dots. So say, for example, this oxygen atom, oxygen has 6 valence electrons, 6 subtract 6 dots, right? The 6 dots, 1, 2, 3, 4, 5, 6 dots, and 1 stick gives you -1. Anyhow, and then we discussed what resonance structures are. And in fact, this structure that I have written here does not accurately describe the reality of what a carbonate ion looks like, because that double bond that I have drawn here, this pi bond, is not localized between that carbon and that oxygen. In fact, some of the time, it's going to be between another carbon and oxygen. So some of the time it might be down here, okay? And then some of the time it might be it might be down here. Okay, there we go. So what does that mean? It means that none of these structures, all 3 of these beautiful, wonderful structures that I just drew, none of these accurately describe the carbonate ion. The carbonate ion is actually a hybrid of all three of these structures, which we call resonance structures. So again, the two electrons in this bond, right? The two electrons, once they're here, then they're here, then they're here. They are delocalized. They are actually moving. I shouldn't say they're moving because they're not vibrating between the bonds, but actually they're shared between all of those carbon and oxygens. And so there's a total of 3 possible resonance structures. So we'll put here three resonance structures for the carbonate ion. Okay, number 44, given several Lewis structures, determine the correctness of the depictions. So this is just more of an FYI thing. She says, make sure every electron is accounted for. So that means make sure you know how to tally up electrons. Given a molecule, be able to determine its molecular shape using VSEPR, which is valence shell electron pair repulsion. And the whole idea behind VSEPR is that electrons like to repel each other. They want to get away from each other as much as possible. So with that in mind, let's take a look at a problem. It says, what is the molecular shape or the molecular geometry of the sulfur dichloride molecule? So let's start by writing SCl2. Sulfur has 6 valence electrons. Chlorine has 7 valence electrons. So 7 times 2 is 14 plus 6 gives us a total of 20 valence electrons. The sulfur must be the central atom. So maybe I'll write it over here. We'll put sulfur. We'll draw a bond to each of the chlorines. Remember, if we go all the way back up here, we said that the halogens like to have 1 bond and 3 lone pairs. So with that knowledge, we will complete the octets of the 2 chlorines, 1, 2, 3, 4, 5, 6, 9, 10, 11, 12. So far I've used up 16 electrons. 20 minus 16 means I have 4 electrons left over. Where should they go? They should go on the sulfur atom because it does not have a complete octet. And so I'll put 1 lone pair up here and another lone pair here. Now my Lewis structure is just hunky-dory. It's great. Okay, now I need to figure out the molecular shape. It is not a linear molecule. I have 2 bonds, right? And I have 2 lone pairs. So that means I have 4 regions of electron density that are going to try to get us as far away from each other as possible. And therefore, they're going to adopt a tetrahedral electron geometry. But remember, there's a difference between electron geometry and molecular geometry. So let's draw the tetrahedron. So I'll put the lone pairs in the plane of the board or the page. I'll have 1 chlorine going in the back, and then I'll have another chlorine atom coming out in front. Now remember, the electron geometry is tetrahedral, okay? But the molecular geometry or the molecular shape involves only what? The bonds only, okay? The lines that I drew to the lone pairs, those are not bonds. The only thing that are bonds here are these. So my molecular geometry is bent, just like a water molecule. This is a bent molecular geometry. The next question says, given a Lewis structure, determine which bond is the most polar. So it'll be the one in which there's the largest difference in electronegativity. Well, you don't have to memorize all the values of electronegativity, but we discussed how in the periodic table, the electronegativity, En, increases going up a group, and it increases going across a period, going from left to right. Therefore, if I think about these elements, I have oxygen, which is going to be the most electronegative element. Remember, any bond between, I don't know why I drew chlorine, any bond between hydrogen and carbon, these are nonpolar bonds. Yes, there is a small difference in electronegativity, but generally speaking, it's a nonpolar bond. Now, if I look at the bond between carbon and oxygen is a polar bond, and the bond between oxygen and hydrogen is a polar bond, I draw the arrow pointing towards the more electronegative element. But if I compare the electronegativities of hydrogen and carbon, now I have these memorized. Hydrogen has an electronegativity of 2.1 and carbon's is 2.5. oxygen is 3.5. Therefore, the difference in electronegativity will be greatest for the oxygen-hydrogen bond. This is going to be the most polar bond. And again, the rationale for that is that delta En, okay, delta En for the hydrogen-oxygen bond is going to be equal to 3.5 subtract 2.1, which gives me 1.4, whereas delta En for the hydrogen-carbon bond is going to be 2.5 subtract 2.1, which is 0.4. So again, this is going to be the most polar bond. So I think what you should know here is that oxygen is the second most electronegative element, and you should know that carbon is more electronegative than a hydrogen atom. Number 47 says, given several Lewis structures, determine the structure that will be polar. And she says here that the hint is that it's usually, it's an asymmetric structure that usually has lone pairs on the central atom. This is kind of a rule of thumb that you can use most of the time. It will work in order to determine which is a polar molecule. If we evaluate all of these, and I'm not going to spend all the time to go through how to draw all of these molecular geometries in gross and dirty detail. This is something you can do on your own time because it's something that we went over a lot. But if I draw all of these Lewis structures out, if I draw the first one, which is SiS2, it has a Lewis structure like this. Okay, if I draw PH3, which is called phosphine, it's going to have a Lewis structure or a molecular geometry, something like this. SiH4, it's called silane. Again, you don't have to know the common name. I'm just telling you as an FYI. Okay, and the last one is silicon tetrachloride. And I'll draw the molecular geometry of silicon tetrachloride. And the first thing you should notice is that, or maybe not the first thing you should notice, but the first thing that I notice is that SiCl4 and SiH4, those are nonpolar because they're tetrahedral, right? All dipoles would cancel in this molecule. It doesn't even matter which way they're going, right? All dipoles would cancel in this molecule and in this molecule. The same thing with this one. The dipole here and the dipole here are going to cancel. So dipoles cancel. Whereas if I look at phosphine, okay, there's going to be a dipole moment. And even if you didn't know the direction of the dipole, you don't even have to know the electronegativity. You just have to know that this is an asymmetrical molecule because it's got a lone pair on the central atom. And let's say I have 3 dipoles going this way. Well, what's going to happen? Overall, I'm going to have a net dipole going in this direction. Therefore, this is a polar molecule, like that. So the answer is pH3. The next one deals with half-lives. This is about the second thing that you would see from chapter 9. The first thing was balancing the equation balancing a nuclear equation using mass numbers and atomic numbers. This involves half-lives. If you've taken mathematics, usually at college mathematics, you'll look at half-lives. So we will revisit that topic in chemistry. There's a couple of ways that you can solve this problem. It says an isotope has a half-life of 8 hours. So we can write our T1 half is equal to 8 hours. If the original activity was 32 millicuries, which again, you don't even have to know what that means really. It says, when will the activity be 2 millicuries? So it's just saying it's undergoing decomposition from 32 to 2. So you could do it like this. You could say, well, I start with 32. If I go 1 half-life, right? So 1 8-hour period, it's going to decrease to 16. If I divide 16 in 2, so that's another half-life, it's going to decrease to 8. If it goes through another half-life, it's going to degrade to 4. And if it goes through a 4th half-life, it's going to degrade to 2 millicuries. Okay? So how many half-lives is this? This is 4 times T1 half. So 4 times 8 hours gives me a total of 32 hours, like that. Okay, that's probably the easiest way to solve this problem. Okay, so after 32 hours, it will go from 32 millicuries to 2 millicuries. The next one, number 49, what time is it? We got a few minutes left. I'll stop at 9:45 so we can just chat at the end. Let me see how many questions do we have left. Oh, we're rocking and rolling here. Number 49, given a reaction at equilibrium, determine what action would cause the equilibrium to shift in a particular direction. So the question or the reaction that we're looking at is this one right here. It says, for the following reaction at equilibrium, which gives a change that will shift the position equilibrium to favor more products. Well, let's take a look here. If my delta H is a positive value, this means this is an endothermic reaction, right? When my delta H is positive. So this means that the energy is a reactant. You have to put energy in to make this reaction proceed. So therefore, we could rewrite the equation up here. I'll put 30 kilojoules per mole plus 2 NOBR. I'm just going to leave out the states of matter just for fun. Anyhow, which gives you 2 NO plus BR2. I think I got all that right. So let's examine what would happen here. It says if we increased the total pressure by decreasing the volume. Oh, shoot. I had to include the states of matter, so I'll put my gas. Everything is in the gaseous phase here. And what's going to happen if we decrease the volume, it's going to shift to the side with the smallest number of moles of gas, because we know that 1 mole of an ideal gas at room temperature takes up, or at STP, at 0 degrees Celsius and 1 atmosphere, takes up 22.4 liters. And so if I look at the total number of moles of gas, on this side, I have 2 moles of NO gas and 1 mole of Br2. So I have 3 moles of gas. But on this side, I only have 2 moles of gas. And therefore, if I decrease the volume, it's going to shift to the side that's going to take up the less space. So it's going to shift to the left. And therefore, it's not shifting to more products. Let's look at the next one. It says, if we add more NO, well, if I increase the amount of NO, it's going to counteract to alleviate the stress that I'm putting on the system, which is basically me summarizing Le Chatelier's principle. So if I increase the amount of NO, it's going to have to shift back to the left to make more NOBR in order to alleviate that. So it's going to shift to the left. In this case, if I remove Br2, it's going to shift to the right, because it's going to have to go back towards the product to regenerate more Br2 and reestablish the equilibrium. So this is the answer, right? This is the final answer, is that one. Let's evaluate the next ones just for fun. The next one says lower the temperature. What would that mean? That would mean I'm lowering the amount of heat energy that I'm putting in, and therefore I'd have to move back to the left to fill that back up. And then same thing with removing NOBR, right? I have to go back in this direction to fill it back up. So the answer is this one here. Okay, let's take a look at question number 50. Why don't we leave this one for Thursday morning? And right now, I'll call it quits with the problem solving. Let me just see here. Stop that. Go into my Teams and stop recording.